And it is a real pleasure to introduce Francesca Molinari. Francesca is the H.T. Warshaw and Robert Irving Warshaw Professor in the Department of Economics at Cornell University. But much more importantly, she is Income Professor at the School of Government and Policy. Will be joining us. She's already working with us now, but will be formally joining faculty at Hopkins next summer. She's currently a co-editor of the Journal of Political Economy and a fellow of the Econometrics Society, where she also serves on the executive committee. And her research focuses on identification problems and proposing new methods for statistical inference in partially identified models. And she's recently started working on problems related to algorithmic fairness, and we're going to hear about that today. So thanks for joining us, Francesca.
Thank you. Thank you so much for having me. It is a great pleasure to join the Hopkins family, and it's also a huge pleasure to be here, get to meet you and talk to you about my research. And also I want to say especially thank you for being willing to listen to an economist. Our seminars are structured in a bit of a different way. Please interrupt me if you have any questions or I'm unclear and the like. So this paper is about inference for an algorithmic fairness accuracy frontier, and this co-authored with my student, Ichi Liu, who is on the job market this year, unfortunately, and he's going to experience a lot of pain, but she's absolutely wonderful, best student I've ever had. So the motivation for this paper is that many decisions are guided by algorithms. Examples include medical treatment, base decision, college admissions, lending decisions, hiring, and the like. But the accuracy of these algorithms can vary substantially across subgroups of the population. An example which has received a good amount of attention in the literature was the early ProPublica finding in 2016 that software used to adjudicate bail decisions appear to be biased against Blacks. That's not the only example. Racial disparities have been reported in automated speech recognition. And this, I always found it to be really frightening, because in the United States, there has been at least some discussion of using AI to analyze inmate phone calls and make decisions again about parole and the like. And if we are in a situation where the software is, where the voice recognition ability is substantially different across subgroups of the population, we may be looking at instances where the decisions are also going to be systematically different across the population, which I find truly frightening. In addition, there are regulatory concerns about the use of AI. Originally, the Biden administration had issued a presidential order about asking the Department of Labor to make sure that algorithms did not discriminate across subgroups of the population, although the Trump administration almost immediately removed those protections, but those protections are still in place in Europe. And so the question that we want to address in this paper is how can we assess compliance to these guidelines, and in particular whether algorithms are in fact not discriminating against subgroups of the population. And so what I'm going to talk about today is an instance where a fairness-minded or a Pareto optimizing agent, for example, a college, is interested in the following questions. Should group identity be banned as an input to the algorithm? And in the United States, this decision has been adjudicated by the Supreme Court, where the group identity is race, where the Supreme Court decided that we cannot use race in college admission decisions. And are there less discriminatory alternatives relative to an existing algorithm? And here what I have in mind is a case of where disparate impact should be adjudicated. And so in disparate impact cases, there is a three-step procedure according to the legal system in the United States. In step one, a plaintiff files a complaint arguing that the current policy, so the current algorithm, harms disproportionately members of a protected class. And then the business provides a justification arguing that the policy is necessary for legitimate non-discriminatory interests of the business, at which point the plaintiff, the ball is back in the plaintiff's court, and the plaintiff should show that there exists a less discriminatory alternative that serves the same interest. And what we want to focus on in this paper is precisely the question, oh, my colors don't show here at all. Well, a little bit, you can see that this is highlighted. Yeah, okay. that is there a less discriminatory alternative relative to the existing algorithm that is being used? And the point that I want to highlight here is that while step one, from the statistical perspective, is relatively easy to carry out because you're just going to compare, for example, some mean of some distribution and use simple t-test to check whether these two means are the same. The last step is actually statistically fairly complex because you need to be able to find another algorithm that is at least as accurate as the one which is currently used and more fair, or at least as fair and more accurate. Okay? So, and another question that our fairness-minded agent may be interested in is how far are different algorithms from the fairest point on the frontier. I will define fairness and I will define the frontier throughout the slides and probably 6-7 minutes from now. And so the point is that you have multiple algorithms that you could be using, and you ask yourself, what are criteria? What are properties of this algorithm that I can use in choosing which algorithm to in fact deploy for my decisions? And we think that the question of how far the different algorithms are from the fairest point on the frontier is something that can be useful for policymakers to decide which one to pick. And what we want to address in this paper is the question of how can you evaluate these trade-offs when at the end of the day you have only finite samples. Okay, and so with finite sample, you need to worry about statistical uncertainty. So before I go further, let me give you some examples of data sets which I think are known in the computer science community, which have been used to think about questions of fairness in some of these data. So these data sets and this specific table is taken from a paper of Berk et al. In 2017, which was in fact talking about fairness. And what I want to emphasize here is that sometimes when we think about algorithms, we think about really, really huge data sets. But the data sets in practice are not that huge. I mean, I'm not saying that they're small, but these examples range in size from 6,000 to 32,000, 33,000. But we use a lot of covariates, a lot of X variables, basically, to do our analysis. And moreover, the minority group can be very, very small in size. And so when we go to estimate conditional expectations and the like on such small data sets, statistical error becomes really a first order question. And that's the type of first order question that we want to address in this paper. Okay, so what we want to do is to propose a new statistical inference method to test the hypothesis that I showed before and to estimate the frontier. Okay, so let me jump into the details of what we do. We built on a micro theory paper by Liang, and Okumura, which was recently accepted for publication in the Journal of Political Economy, which is one of the top 5 general interest journals in economics. And this is a purely theory paper that assumes that all the distributions are perfectly known. The distributions of the observable variables are perfectly known and characterizes a fairness accuracy frontier. So we're going to take the structure of the fairness accuracy frontier from this paper. And then we're going to provide a toolkit to do the following things: consistently estimate the fairness accuracy frontier and build a confidence set for it. So I'm going to give you an estimator of this frontier, and then I'm going to put a little sausage around this frontier, which is going to be my confidence set. And test the policy relevant hypothesis that I showed before, which were, should group identity be banned, and are there less discriminatory alternatives relative to the algorithm that is being currently used, and to consistently estimate the distance of any algorithm from the fairest point on the frontier. Now, all these things are done in the paper, but here, in order to actually not go over time or not too much over time, I'm just going to focus on the consistent estimation of the frontier and the test for the existence of a less discriminatory alternative. And then to try to make it all concrete, I'm going to illustrate these results by revisiting the empirical study in the Science 2019 paper of Obermeyer, Vogeli, Peters, and Mulanathan, which looked at a research hospital that uses an algorithm to assign high-risk patients to a more intensive care. Okay. So this is an outline of the talk. I need to start by giving you this theoretical framework from the paper of Liang and co-authors in order to understand the structure that we built on. And then the other points on this slide are our innovations in this paper, our contributions. But the first point is simply explaining the structure that we borrow from this theoretical paper. I'm going to use my empirical application to motivate all the notation. And so hopefully make the entire discussion more concrete. Again, please ask questions if anything is unclear, especially in the notation. Okay? We're going to look at the population of individuals, which is described by the following variables. There is going to be some outcome variable y. In our example, it's going to be the number of active chronic illnesses in the subsequent year for this population of patients in the research hospital. Okay? I'm going to have a group G, which I'm going to call red and blue throughout the theory part of the talk. In our empirical application, is going to be race, and we're going to have white patients and black patients. And then I'm going to have a vector of covariates X, which are going to be the inputs to the algorithm. And I want you to have in the back of your mind that this vector of covariates is going to be high dimension. Okay? So in our application, we're going to have about 48,000 observations, and we have 149 covariates. And given that we want to do everything non-parametrically, it is really quite a large set of covariates. And the example in the medical context is that X could be age, gender, comorbidity and medication variables, cost, biomarkers, and the like. Okay? Now, each individual is going to receive a binary decision, lowercase d, which can be 0 or 1. It's going to be 1 if the individual is automatically enrolled in the high-risk care management program, and it's going to be 0 otherwise. And we're going to have an algorithm A, which maps the space of covariates X into 0, which basically the goal of this algorithm is to predict the probability of an event. And the event in question in our empirical application is whether the patient is going to be very sick next year. And very sick in the application is defined as a number of chronic illnesses in the subsequent year that exceeds the 97th percentile. Because the way that this hospital works is that if you are at that level of sickness, so you're above the 97, you're in the top 3% tail of the distribution, you're automatically enrolled in this high-risk care management program. If you're below the 97th percentile, they basically, between the 55th and the 97th, they look for a doctor's opinion. Below the 55th percentile, you just don't get enrolled. Okay? And so this prediction A of X determines the probability with which the decision equals 1. Okay? And the important feature here is that the group identity is not an input to the algorithm, okay? And then the final piece that we need to define things here is some loss function, which is going to be associated with the algorithm. Sorry, some loss which is associated with a given algorithm, and the amount of loss is going to be measured through a function calligraphic L, which maps D and Y into R. And in our empirical application, it's just going to be classification loss. Yes?
What's the justification for why the group isn't in the set of covariates?
So the idea is that often the group is not allowed by regulation to be in the set of covariates. I will talk. So one of the things we want to test is whether it would be, well, I'm not going to show that test here today, but one of the things we do in the paper is to provide a testing method for whether allowing the group to be part of the inputs to the algorithm would uniformly increase welfare. But I'm not going to be able to do it today. There are some technical things in the estimation and asymptotic theory that becomes more complicated if you allow the group, and I'm happy to discuss that.
Thank you.
So now, one key ingredient for the development that we do here is to think about what I'm going to call group risk or group expected loss. So take a group G, generic, little g stands for a generic group, and it can be red or blue. For this group G, I'm going to define the expected loss, just in the standard way, is the expected value over y and x of the loss when the decision is 1, multiplied by the probability that decision is 1, which is a of x, plus the loss when the decision is 0, multiplied by the probability of the decision being 0, and then conditional on group being little g. So I take the red people, I compute the expected loss for them, the blue people, the expected loss for them. And so given an algorithm, so the algorithm designer chooses the algorithm, and once you have that algorithm, based on the joint distribution of y, x, and g, we obtain the expected loss associated with algorithm A for the red people and for the blue people, and this is going to be a point in R2, okay? Now, as I look over all possible algorithms, again, these all possible algorithms is the collection of all functions that map x into the interval 0, 1. I'm going to obtain a feasible set of group risks, and how is this feasible set defined? Is that I take these points in R2 associated with a specific algorithm A, and I collect all the points as I take any possible algorithm A of x, so any possible function that maps x into 0, 1. The original, so this set A is going to depend on the distribution of the data, bold P, and on the space of algorithms. So far here, I'm looking at completely unrestricted space of algorithms. In the appendix in the paper, we consider different type of restrictions, like the algorithm has to be a linear function. The algorithm has to be a threshold rule, meaning if A of x is above a certain threshold, everybody receives d equal to 1. If it's below, everyone receives d equal to 0. We show that all our results apply also in these cases. But here I'm just going to consider completely unrestricted class of algorithms. And so I'm going to drop in the set E the dependence on P and calligraphic A of x to keep the notation mildly less abominable. And in the original paper of Liang, and Okumura, they prove that when x and y both have discrete distribution, this set calligraphic E of x, calligraphic E is a convex set. We extend this convexity result for any kind of distribution of x and y, and convexity will play a key role in all the asymptotic theory that we do here. So this approach kind of like really relies on convexity. Okay, so now in order to talk about frontier, I need to define preferences, okay? And so I'm going to consider two types of algorithms. So suppose that there are two possible algorithms. What am I doing here? I better look in the screen. There are two possible algorithms, A and A prime. A implies expected losses E prime, and the other algorithm implies expected losses, sorry, A has E, A prime has E prime, okay? And so now the preferences work as follows. We say that the first algorithm is preferred to the second if it is more accurate in the sense that the expected loss under the first algorithm for the red people is less or equal than the expected loss under the second algorithm, same for the blue people. And fairness is defined as the difference in expected losses across the two groups under the first algorithm is less or equal than the difference in the expected losses for the second, under the second algorithm, okay? So which means that the algorithm, well, I will prefer in terms of fairness one algorithm over the other if the discrepancy in accuracy between the two groups is smaller under the first algorithm than under the second algorithm. And so then what is the frontier? The fairness accuracy frontier is the set of points E in the feasible set such that there does not exist another algorithm that gives me an expected loss that is at least as small for each of the two groups and more fair, or at least as fair and more accurate, okay? This F also depends on the distribution of the data and on the algorithm, but I'm again suppressing that dependence. Now you could say, well, I don't want to deal with this fairness criterion. I just care about Pareto dominance. If you only care about Pareto dominance, the description is essentially the same as before, except that we remove the fairness criterion, okay? And in the paper, we derive all our results also for the case that you only care about Pareto frontier. So let me begin to show you graphically a little bit how things look here. The feasible set in our problem is going to be convex. In fact, it's going to be strictly convex. And I'm just going to, for simplicity, visualize it as an ellipsoid. Okay. And there are going to be some particularly important points on this feasible set. The point capital R corresponds to the expected losses that you can realize if you care the most about the red people and the red group, and you pick the algorithm that minimizes expected loss for the red group, and it's going to end up being this. Okay. There is a similar blue point, capital B, which is the one that corresponds to picking the algorithm that prioritizes the blue group and minimizes the loss for the blue group. And in this picture, the fairest point is going to be this point here on the boundary of the feasible set, which is the point that is closest to the 45-degree line, because that's the point that minimizes the discrepancy between the two, the accuracy of the two groups. Okay. Okay, now this is the last result that we take from this paper of Liang, and Okumura. And what this result does is to give you a mathematical characterization of the fairness accuracy frontier. Before I gave you this fairness accuracy frontier in some sense in an abstract form. I said the frontier is going to be all the points E, is going to be comprised of points E, for which there does not exist an algorithm that gives me something at least as fair and more accurate, or at least as accurate and more fair. But while that is a very clear conceptualization, it's not something that you can bring to estimation in an easy way, because to estimate, you need to something that looks like a sample mean or something like that, okay? So we want to transform that theoretical characterization into something that we can take to the computer and estimate with finite data. So what this authors show, Liang et al., is the following quite neat property, I think. Oh, okay. So what this concept of group balance means is that if the red point and the blue point lie on opposite side of the 45-degree line, then the fairness accuracy frontier coincides with the Pareto frontier, and it's the function of the boundary of the set E, which is closest to the origin, and that joins the point R to the point B. And the more important message here is that in this case, it coincides with the Pareto frontier. On the other hand, if the data, this is purely a data question, exhibits what they call group skew, then where group skew means that the point R and the point B lie on the same side of the 45-degree line, I'll explain conceptually what that means in a second, then the following sort of strange phenomenon occurs, that the fairness accuracy frontier includes the Pareto frontier, which is the portion between the red point and the blue point, but then has an upward sloping portion where actually the allocations are Pareto dominated, because you are increasing, you are worsening the accuracy for both groups. But the policymaker that cares about fairness is willing to go in that direction because it increases fairness. Okay? So what does group skewness mean? And of course, we have a counterpart for the case that R and B are both below the 45-degree line. What this conceptually means is that the data distribution is such that even when you do the best possible thing for the red people, the accuracy of the red people is still less than the accuracy of the blue people. So in a sense, the data, you know, the reality of the universe is skewed against the red people in this picture and the blue people in the previous picture, okay? And so in that sense, when you find yourself in that situation, you may be willing to give up on accuracy depending on the preferences of the policymaker for both groups in the interest of making the universe a little bit less unfair against the red people. Okay? A pure economist would say that this doesn't make too much sense, that you would give up on accuracy for both, because why should we all be worse off? But it is consistent with this concept of caring about fairness. Okay? Okay, questions about this is the setup. Any questions about this? Okay, so now let me jump into what we do. So in this picture again, I have plotted my convex feasible set of expected losses associated with all possible algorithms. And now I need to, the frontier is a part of the boundary of this set. And so the first piece of mathematical tool that I'm going to use to be able to come up with an estimator that will mildly resemble a sample mean, of course it's not going to be a sample mean, but at least vaguely, is to give you a mathematical tool to describe the boundary of this feasible set. Okay? The standard mathematical tool to describe the boundary of a convex set is its support function. What is the support function? The support function is the sign distance. So the support function, so when you talk about support function, you need to first pick a direction. And so let's say that we pick this direction pointing down, which corresponds to the vector 0, -1. The support function is the sign distance between the supporting hyperplane to the set E in this direction and the origin. Okay? And so in this example, it pins down the vertical coordinate of the blue point. Okay? But the vertical coordinate of the blue point is not sufficient. I also need the horizontal coordinate of the blue point. And how do I get that? I get it from working with the next, the sibling of the support function, which is the support set. And what is the support set? The support set is the intersection of the set you care about with its supporting hyperplane. And under the assumption that this set E is strictly convex, meaning it doesn't have flat faces, it's going to be the unique point, which is going to coincide with the point B. And the important feature of this support point is that I can fully describe it from the support function of the set, because it's given by the intersection of the hyperplane with the supporting hyperplane in direction Q, that it's completely pinned down by the support function, and the set itself, which is also completely pinned down by the support function, because a convex set is given by the infinite intersection of the closed half spaces that contain it, and these closed half spaces are pinned down by the support function. Questions about that? Where am I going with this? Where I'm going with this is that in a minute, I'm going to give you an estimator for this function h e of q, which is going to look like a sample average, actually. And once I have this estimator for this h e of q, I'm going to do all my analysis, all my test of hypotheses, the definition of the frontier, and so on, as restrictions on this function h e of q. Okay? And that's why it's important to show you how it pins down the points on the frontier. Okay, so now I want to show you that this support function is going to be just a conditional expectation. And again, why that is useful, because we all know how to estimate conditional expectations, and so I can use all that knowledge to go back to my frontier. Okay, so in order to and as I show you that, I'm also going to be able to show you which algorithm correspond to points on the frontier, which turns out to be an important question later in this context. Okay, so I want to show you the form of the support function. To do that, I'm going to remind you that I have two groups. A generic group is indexed by G, and the two groups are red and blue. I have two decisions, 0 and 1, and I'm going to define a conditional expectation that throughout I'm going to denote by theta dg of x. And what's this theta dg of x is the conditional expectation of the loss function multiplied by the indicator of the group, conditional on x. Okay, I'm going to call this product the loss function, the indicator of the group. I'm going to call it my effective label. Okay, and what I'm going to do later on is to estimate this conditional expectation through a machine learning method. I could use the lasso. And actually in our empirical application, we use random forest, but this is just a conditional expectation. There is nothing fancy into estimating this, except that x is I-dimensional, and so I want to do this in a smart way. Okay. And then mu G is just a fraction of people in group G. And I'm actually going to drop it in a minute because I don't want to carry this thing around, but I do have to remember eventually that I'm also estimating this thing. Okay. And so now I'm going to remind you of my expected loss. Okay. My expected loss is here. That's the definition we had before. And the first thing that I'm going to do is I'm going to use the low iterated expectation to rewrite this expected loss in terms of the theta functions, okay? And this is just an algebraic manipulation that uses the low iterated expectations. And so then I can separate it out in two pieces, a piece that does not depend on the algorithm at all, and a piece that depends on the algorithm. All I've done here is that I pulled out theta 0 of x, which is the part that does not depend on the algorithm. And then I have expected value of a of x times the difference in the theta functions. Heuristically, you can think of the difference in the theta function as some kind of conditional average treatment effect, right? The difference in the expected value of this effective label when the decision is 1, conditional on x, minus the expected value of the effective label when the decision is 0, conditional on x, okay? And I'm going to ignore the fact that I need to estimate. Oh, yes, Celia.
So you said I could think of this as decayed.
Yeah.
Might it be that this decayed surface is finite dimensional or not for you?
Might it be that this Kate is what?
Can I describe the surface for decayed in infinitely many parameters or not for you?
No, the Kate is non-parametric.
Ooh, okay.
So that's my entire, like not the entire, but a lot of my problems and my challenges come.
Yeah,
from
because you
that.
can't use standard theory for that.
Yeah.
Yeah.
Exactly. If I'm willing to assume that it's parametric, then a lot of my technical problems disappear.
Yeah, you could just use name and orthogonality and you're good. You're off to the races, basically.
Absolutely.
Yeah.
Okay. Okay, so that's my form. And this form will play a role in the next slide, okay? So I dropped the mu G business because it's not interesting and it's just complicates things. So here at the top of this slide, I'm reminding you the form of the expected loss. And I'm reminding you the fact that the set calligraphic E takes these expected losses for the red and the blue group for a given algorithm A and takes all the expected losses across all the possible algorithms. Now, the mathematical form of the support function, I didn't spend a lot of time before, I was just mostly showing you the graph, but the mathematical form is that the support function of the set E in direction Q is the following. It takes the maximum over little e in calligraphic E of the inner product of Q and E. Okay, that's just the functional form of this object. And it's gonna give you basically the intercept of the supporting hyperplane in direction Q, okay? So now I plug in this expression here, I plug in this expression for the support function, the expression for a generic E, and I recognize that as I move across algorithms, all what I'm doing is that I'm taking the maximum. So this maximum over E in calligraphic E corresponds to taking the maximum over functions in calligraphic A of x of the expected value of A of x times Q transpose the difference in the theta functions, okay? And while this at first look appears like a really complex problem because I'm taking a maximum over a space of functions, so who knows what that would look like, in our problem is very easy because because these functions, they map calligraphic x into 0, 1. So what you're gonna do is that you're gonna choose A of x to be equal to 1 if this inner product is positive, and A of x to be equal to 0 if this inner product is negative. Because that's what's going to give you the largest possible value for the inner product of Q with E. And actually, this expression had eluded me for many, even though it's very simple, the connection that this is actually an algorithm, this indicator of Q transpose theta 1 of x minus theta 0 of x greater than 0, is itself an algorithm, had eluded me for the longest time, until Gillian told me that I should figure out that in a court of law, they would want to know the algorithm that actually improves over an existing algorithm, puts you on the frontier and so on. And that Gillian's conversation gave me the motivation to try again to figure it out. And then once I figured it out, I was like, oh, this was so simple. Why didn't I say it before? But you know how that goes, right? Once you see things, they all look easy. It's the before seeing them that is the problem. Okay. So this is going to turn out to be the algorithm that puts you on the frontier. And versions of this algorithm with very careful choice of Q are going to be the algorithms that improve over whatever existing algorithm that is. And so are going to be the algorithms that you're going to bring to a court of law. Okay. And if now I apply low iterated expectations in reverse, so to speak, I can make it become the expected value of Q transpose L0, where L0 is the function, the expected value of which is theta 0, the conditional expectation of which is theta 0, times Q transpose L1 minus L0 times this indicator. So now going back to the estimation, what you will do is that with finite sample, L0 and L1 are, you can think of those as effective labels or outcomes that you observe. And so you're going to average over those. And in the first step, you're going to have to non-parametrically estimate the functions θ1 of x and θ0 of x. Unfortunately, you need to pass them through the indicator function. That creates headaches because the indicator function is not smooth. And so the way that we estimate this in practice is that we use sample splitting and cross-fitting. Okay, so we take a certain fraction of our data, say 80%, and on this 80%, we estimate these functions theta, okay, through random forest. And then we take the remaining 20%, and for that 20%, we take the observed outcomes, the L0 and L1, and we plug the observed x values in these theta functions that we have estimated on the other piece of the sample, and then we average. And then we keep crisscrossing what's the 20% and what's the 80%, so that we take all the subgroups, and then we do a final average of that. This is standard in debiased machine learning literature. So we didn't invent anything. Once we arrive here, in terms of the criterion we use to estimate, we didn't invent anything, okay? And so what this is supposed to show you is that this thing does look like a sample average, okay? Will be replaced by sample average with a first step, which is non-parametric. And so then what we prove in terms of asymptotic properties of this estimator of the support function is that provided that we can estimate these theta functions at the rate of n to the minus 1/4, so that's going to be one of our restrictions for Ilya's question from before, what we can show is that the estimated support function converges to a Gaussian process. And this convergence to Gaussian process is very important because that's what's going to give us the asymptotic distribution of our estimator. And that's the building block to actually carry out test of hypothesis, because when you want to do test of hypothesis, you need a test statistic, and then you need to be able to compare it with some critical value that you are going to take from the limit distribution of the test statistic. Okay? Questions about this? Okay.
So, but you can't in general get these. So sorry, maybe I misunderstood. What's like the big assumption that lets you do this? Because you don't get anything good in general, not parametric. Okay?
The big assumption that allows me to get this, so what happens is that these theta functions here get estimated at the rate of n to the minus 1/4. If life was, I mean, the assumption is that you can estimate the theta functions at the rate of n to the minus 1/4. Okay. That is a standard non-parametric estimation problem. You need some kind of sparsity underlying the structure of the theta function. If these theta functions were known, then it would be obvious that you get square root of n convergence rate on this estimator. The challenge is to show that the non-parametric rate here is not gonna come back to affect the rate of convergence. And the way that we do that is through Niemann orthogonality. That's step one. And step two, which is actually much harder. Niemann orthogonality is fairly easy in this problem. Well, whatever, less hard in this problem. What's really difficult is to show that the remainder term also vanishes relative to square root of n. And that's where all our headaches come from. And in this regularity conditions link that we can talk about later, the key regularity condition that we assume on the theta function is that it is separable in three parts. Something that depends on the first covariate only, something which can be non-parametric, but it has to isolate the first covariate, something that isolates the second covariate, and then something that can have all the other covariates in any form you want. And the reason why that is important, and these two covariates that are separable, they have to have a jointly continuous distribution with a bounded density function. And what that allows is effectively, with some effort, it allows us to smooth the indicator function. And then things follow from vaguely standard arguments in the debiased machine learning literature.
Gotcha, thank you.
Okay, so now the key, like the cute thing I like here is how do I characterize using the support function is going to be my key mathematical tool. And now I need to characterize the accuracy frontier using the support function. Because what the support function per se just gives you the entire boundary of this set, but I want a specific piece of the boundary. And I don't know whether I'm group skewed or group balanced, and I don't want to pretest for that because pretesting is bad. And if you can, you want to avoid it. So the way that we show that you can do this is by using the separating hyperplane theorem, actually. So going back to elementary arguments. And we're going to create some set C, which is both a proof device and an element of our test statistic. And what this set C is going to do is going to be some set in R2 that is going to collect vectors with a horizontal component. I forgot something important. Suppose that you want the fairness accuracy frontier is the collection of points E star that one cannot find another point that is at least as accurate and more fair, or at least as fair and more accurate. So imagine that you want to check whether a candidate point E star that you have thought about belongs to the frontier. So what you're going to do is that you're going to calculate this set C, which takes points in R2, which have the horizontal coordinate less or equal than the horizontal coordinate of E star, vertical coordinate less or equal than the vertical coordinate of E star, and the difference in the two coordinates in absolute value less or equal than the distance in the coordinates of E star. So this set C collects everything that would quote unquote kill the point E star, because if these points are feasible, then they're better than E star in a fairness accuracy sense, and that means E star cannot be on the frontier. Graphically, I plotted here with these two green polyhedra, the very simple polyhedra for that matter, the set C. Those things here are the set C for two possible allocations of E star. And now I'm going to put together with this set C the feasible set. And look at the difference between the two panels. What we established rigorously in the paper is that if E star is on the frontier, then the pink set and the green set can be properly separated. Their only point of contact is the point E star itself, and their relative interiors can be separated. If instead the point E star is not on the frontier, it may even be on the boundary of the feasible set, but it's not on the frontier because in this picture the frontier goes between the point B and the point R, then this set C in fact cannot be properly separated. And so that's the key result, because you can express proper separation based on the support function. In particular, two convex sets can be properly separated if and only if there exists a direction Q such that the support function of the first set in direction Q is identical to the negative of the support function of the other set in direction minus Q, just separating hyperplane theorem, right? One set is completely inside the above hyperplane and half space, and the other one is completely inside the below half space, okay? And so now going back to the idea that I want to build a test statistic based on some sample average that I can estimate and so on, is what's going to be the frontier. The frontier is going to be given by the point E star in the feasible set such that this criterion is satisfied. So the mathematical way to say there exists a direction Q where this equality holds is the same as to say that the maximum over all directions in the unit sphere of this difference is less or equal than 0. And that's what we're writing here. And why is that helpful? Because I can estimate this guy at the rate of square root of n. This guy is just the value that I want to test against. And so then it's just the same as estimating, well, not the same, but it's the same principle as testing that the mean is equal to specific value. Okay? And what we do in the paper is that we derive the asymptotic distribution of this test statistic, and then we can take the critical values from it, and we prove that the critical values of this test statistic can be consistently estimated by a certain bootstrap procedure. Okay? Questions about this? Okay, I'm going to skip well, when I want, let me not skip, but let me also be careful with time. So now, when we want to test the hypothesis as restrictions on the support function, let's remember why we did this. One thing was to purely estimate the frontier, which I just gave you an estimator, and I verbally told you that I can get the asymptotic distribution of this estimator and therefore build a confidence set around it. I'll show you in the empirical application what this looks like. The other thing we wanted to do was to say there is some existing algorithm that gives me expected losses E star, and now I want to test whether there does not exist a fairer allocation that does not sacrifice accuracy, okay? Against the alternative that there exists a less discriminatory alternative. And so what this means is that I want to test that E star belongs to the frontier against the alternative that it does not belong to the frontier. But I just showed you the how to do that through the separating hyperplane theorem before. And so what we're going to do is that the null hypothesis corresponds to this function taking a value of 0, and the alternative is that it takes a value not equal to 0. And what we show in the paper is that by replacing sample analogs inside of the of these objects in the null hypothesis, we can obtain the asymptotic distribution of these test statistics, and then we prove that a certain bootstrap procedure consistently estimate the critical values of this test statistic. Questions? Okay. So then let me zoom in for a second on the specific algorithms that give me a point on the frontier, and then I'll show you the empirical application. Also, because I want to draw your attention to specific features of algorithms that I can compute that put me on the frontier for sure. I'm going to consider a situation where I have a training sample that includes the outcomes, the group, and the covariance. So in the training sample, I have all these variables. Okay, I'm going to estimate theta through my debiased machine learning estimator, and I'm going to denote the estimator by theta hat subscript n1 to denote the size of the training sample. And then I'm going to have evaluation data. So the hospital would use previous time results of their treatment, which include actually looking at how people of the two races fared when treated with decision 0 and treated with decision 1. But now when new people come through the hospital is only going to use the covariates that they observe for these patients and not the race information to decide where to assign them, okay? So now the algorithm that we're proposing is an algorithm that is going to be based on the training in sample 1, that is going to take the covariate of the evaluation sample and some direction Q. This direction Q basically represents how much you care about the red group and how much you care about the blue group. And I'll have more to say about this in the empirical application. And the algorithm is going to say, you're going to assign treatment 1 to this person with covariance xj if this inner product is positive, and you're going to assign treatment 0 otherwise. And now the loss that the individual j in the evaluation sample is going to experience is just going to be the loss basically associated with the specific decision. And what we prove in the paper is that, in fact, I'm going to skip the full description of the notation here, but verbally what we prove is that, in fact, using this empirical success rule, because this is just an empirical success rule, this algorithm is simply an empirical success rule, we are going to, in fact, be put on the frontier in sample of the sample analog of the feasible set. Okay? Okay, so now let me try to bring it all together through the empirical application. So we revisit this Obermeyer and co-author study. And so what they looked at is a situation where an algorithm is used to determine it to automatically enroll patients in a high-risk care management program. Important, what was the hospital doing before Obermeyer and co-authors came in? What they were doing was to predict total medical expenditure, okay, based on previous healthcare use. They did not use group identity at all. They just looked at people's previous medical care use, and they compute that's what the algorithm was trying to predict. And then the algorithm outputted the health risk score S. And this health risk score S was supposed to be a measure of the health status of people. So because the goal was to predict who will be sick, and the idea is if I'm very sick, I use a lot of medical care, and therefore I have high expenditure, and therefore I need high care management. That was the idea in the original algorithm used by the hospital. And then it automatically enrolled patients if the score was above the 97th percentile. Now, we don't have the original data from the hospital. Of course, this data is heavily private. But the interesting thing is, what's good for us is that Obermeyer and Cotters put synthetic data in GitLab, and that's what we used. We have a total of about 49,000 observations, of which about 5,500 are Blacks. And we have 149 covariates, X variables, and in addition, the black and white indicator. And so you can imagine that we have 149 covariates. And for the smaller group, is only 5,500 observations. To predict well, the theta function is actually very difficult. Okay? And we use classification loss as our loss function. And the outcome variable is whether the actual number of active chronic illnesses in the subsequent year is greater or equal than 6. And the number 6 is chosen because that is the top 3%. So it's the 97th percentile of number of chronic conditions. And we estimate theta of X through random forests. Okay, so now let me show you what does the feasible set look like. The feasible set looks like an ellipsoid, as I showed you before. And here, the purpose of this picture is simply to remind you that this is based on the support function approach. And so these are just supporting hyperplanes around it. Then here I zoom in to show you the actual frontier. It turns out that the expected loss for the red and the blue people, the vectors of expected losses at the R point and at the B point are actually identical. But that's not good news because they are below the 45-degree line, both of them, okay? The 45-degree line, I don't know if you can see it, but it ranges here. The vertical axis is the expected loss of the white people. The horizontal axis is the expected loss of the blue people. And this sort of shaded area around is what okay? Oops, I didn't mean to do that. This shaded area around is my confidence set, okay? So clearly, this data is skewed against Black people, because even at the point which is best for the Black people, their expected losses are higher than for the white people, okay? And the fairest point, which is this black dot here, in fact, increases the expected loss for both groups. I'll come back to that if I have time, okay? So that's the structure. And now what Obermeyer and co-authors do is the following. They point out that the algorithm used by the hospital aims at predicting, at using costs as labels to predict health needs. That naturally is not, at least in hindsight, is not a great idea, because the amount of expenditure that you have is influenced by the type of insurance that you have and different cultural approach to the use of medical care, which can be very different across different subgroups of the population, especially in the United States, okay? And so these observations are already in the Obermeyer paper. And so what they do is that they propose two other algorithms, which are that they propose to think about other possible algorithms that this hospital could have used instead of this one, which is based on predicting cost, which is not a good measure to predict actual health needs, okay? So they propose two other algorithms which are still trying to predict costs, and one algorithm which is trying to predict the number of active chronic illnesses directly, okay? And so what do I plot in this picture? What this picture plots is, again, my frontier, which is from the black dot to the blue dot, along with the confidence set. And then this green asterisk here is the original algorithm that the hospital is using. And as you can see, it's pretty far from the frontier, actually. So we can soundly reject the hypothesis that this algorithm is on the frontier. The diamond with the crossed diamond is another algorithm that uses total costs as effective labels. And this filled out diamond over here is yet the other algorithm that is based on costs. And so the takeaway message from this portion of the picture is that predicting cost is not a great way to try to figure out who is going to be sick. Cost labels are not great to figure out who is going to be sick, again, because of issues related to the fact that who has good health insurance will use more health insurance. Okay? The empty diamond here is actually the algorithm that predicts accuracy, that predicts the number of active chronic illnesses, okay? And that one puts us smack on the frontier, and in fact is working quite well in terms of accuracy, okay? And we cannot reject that is on the frontier, of course. Okay, so now let me conclude by telling you something a little bit, again, this part would not exist if I didn't talk to Jillian. How does our algorithm, our empirical success rule, is it useful? Okay. For our empirical success rule to be actioned in practice, you need to choose the direction Q. And the direction Q can be interpreted as a planner's, how much a planner cares about the red group and the blue group. Okay, it's basically its weights on these two groups. In addition, if I want to show you how this algorithm works on the hospital data, I also need to constrain myself to treat only 3% of people. Because of course, if I treat the entire population, maybe my outcomes would look much better, but that's not an apple-to-apple comparison. So in the paper, we figure out how to also do this constraining. It's explained in the paper. I won't get into the details. But I just want you to know that we're taking this into account. And now I'm going to consider 4 different directions Q. So 4 different ways to weight the two groups in my algorithm. One is what we're going to call Rawlsian. And so this is a preference for the minority group. And so this would realize the R point. So sorry, the best possible, this is the algorithm that will generate the least expected loss for the Black people. The other one is based on majority, and so it will generate the best possible outcome for the white people. This egalitarian is going to be the algorithm, the direction Q, that would pin the fairest point on the frontier, which is this black dot here. So it's going to be the direction such that it would give me this point F. And then the other thing that we're going to look at is just simply utilitarian. Everybody is the same. I put the same weight on both of them, okay? And so we assess how this algorithm's ability to assign sicker patients to treatment. Because what I want at this stage is to say, is this algorithm actually going to do a good job at pulling out who should receive treatment, okay? So now I'm going to show you some pictures. The first one is taken from the Obermeyer paper, and the others are our pictures. They are all in the same page, so I need to walk you through what's there, and it's also kind of small, sorry about that. Look first at the top picture, okay? This top picture is literally replicated from the Obermeyer paper. It has on the x-axis the percentile of the algorithm risk score, okay? And then this vertical dashed line here is the 97th percentile. So what happens in this medical hospital right now is that people in this sliver here are automatically assigned to treatment and nobody else is, okay? The yellow line here corresponds to, so the vertical axis is the number of active chronic conditions. And the yellow line is the number of active, so is this number of active chronic condition for the white people. And the purple is for the Black people. And so one of the messages of the Obermeyer paper was that the algorithm systematically did not assign to care people, Black people who were more sick than white people, okay? Now the two bottom panels, and I will actually conclude with those because I'm at time, use our algorithm, okay, to assign people to treatment. So this is the majority and this is Rawlsian, okay? So this privileges the Black people, this privileges the white people. Let me explain what's on the graph. These two curves at the bottom, the sort of pinkish ones, are represent the number of chronic conditions against the percentile algorithm risk score of the original Obermeyer paper to try to make these pictures comparable, although this thing doesn't play any role in our paper, okay? And these are the people who are not treated. Our algorithm would say Q prime theta difference is zero, therefore it's less than zero, therefore I don't treat these people. And here you have the same discrepancy between black and white as in the original data, because that's inevitable, right? I'm only treated 3%. This is 97%. This is the difference in the overall population, so that difference cannot be avoided. But the top graph is the treated people. Purple is the black people, and yellowish is the white people, okay? And what is the takeaway message here is that our algorithm, first of all, identifies people with very high level of chronic conditions later on. And even if the score, the percentile of the algorithm score is very low, it still figures out that those people should be treated because they're going to have very high number of medical conditions. And second, displays basically no difference between the black and the white people, okay? Let me conclude. No literature. There is a large literature, as you probably can imagine, and you probably already know. So what we do in this paper is that we take the theoretical framework of this Liang et al. Paper as our starting point. In that paper, they derive all the characterization of the frontier, but they assume that all the distributions of the observable variables are exactly known. We realize that in practice, we only have finite data. And so we provide a toolkit to consistently estimate the fairness accuracy frontier and put a confidence set around it, build algorithms that are on the frontier, and test the policy relevant hypotheses that I described before, like should group identity be banned, are there less discriminatory alternatives, and how far are we from the fairest point on the frontier? And then we illustrate our results by revisiting the empirical study of Obermeyer and co-authors. Thank you so much for your attention, and any comments, please email me, and the paper actually exists.
Any questions? Yeah, so I actually had a very long discussion with Ziad Obermeyer. We're good friends, and we're trying to recruit him here at the School of Public Health.
I think that it's gone well, from what I hear. Not well? I just was told that it's gone well.
It is. So the problem that in the paper is that there is, from an epidemiological point of view, there is the origin population, there's the source population, there's the study population. And we're trying to make inference from the study population all the way to the origin population. When they use the claim data set, which is a cost data set, it's a proxy of care. It only reflects those who came to the hospital. It doesn't reflect the epidemiological incidence of the disease. So it's a sampling problem from an epidemiological point of view. But at the same time, if a hospital is trying to predict resources to care for their catchment population, and let's say 50% of their catchment population can access that care, then the prediction should match the cost data set. Unless in the future, access to care improve, which means there was a shift in the joint distribution of the input data set, which what happened in Ziad Obermeyer. But at the same time, even the white people in the data set, they are still underrepresented by their true incidence of disease. So if we equalize everyone in equal weight, we're still not reaching the true potential of what patient brings in.
Yeah.
The question is, how do we really estimate the true need, not just by the data it's giving us? Because I think we are far away from the truth.
So I think you, if I understand you correctly, you raised two different issues. One issue is basically that we've selected labels.
Yes.
We observe only the outcome for people who did come into the hospital. So we assume the way the selective label problem in this paper, but I'm working on a next paper which looks at the selective label problem. Now, there are two things that you can do. So the problem is clear, right? You observe the outcomes for people who can come to the hospital. but there might be a bunch of other people with a different distribution who don't even come to the hospital, maybe because they don't have any insurance at all or whatever. And so the sample that you observe is selected. So it's a standard sample selection. So there are two things at least that you can do. One would be a relatively straightforward generalization of what we have here, which is to assume that conditional on a perhaps even richer set of covariates, the selection is ignorable. And then you need to do some inverse probability weighting or some other methodology to deal with that. What we are doing in what I'm at the moment a bit more inclined to look into is a situation where I recognize that there is a subset of the population that I just don't observe, and that could be not random, even conditional on covariates. And so what happens is that the frontier is actually not point identified, but the frontier is only partially identified. Think that the frontier itself is some kind of saucer. And so what we are trying to do is to do this for that case. And of course, it presents technical complications that we're working on. So that was your first question. The other question, I think, was having more to do with some sense of budget constraint for the hospital, right?
Yes.
Yeah, so that I've not touched yet. Although I've had the following thought that I would like to work on, which is that in some sense, what the hospital, I think, would like to do is to have some kind of, let me simplify a little bit. The problem you're describing is super complex, is that the hospital wants to be on the frontier, but it wants to minimize cost. Or anyway, keep cost under control. So let me try to verbalize that as minimizing cost. And so what I'm hoping to do in the next project is to figure out how can you pick an algorithm that basically satisfies two criteria. One is that it puts you on the frontier, but the other is that, like, imagine that you're trying to, you have the feasible set and you want to be in a certain wedge of the boundary of this feasible set, but at the same time, while doing that, you want to do the thing that minimizes cost, or reversing it maximizes profit. If, for example, you are an insurance company who needs to figure out how to price insurance. And so that's how I'm thinking to approach your question.
Yeah, so the hospital will get like a capitation insurance program. So there will be, let's say, 100,000 people for a lump sum of money. The hospital need to care for those 100,000 people within the limit of that budget, but also get the best possible outcome for most of them. So there is a budget constraint, and there is also number of people limit, and you have to maximize the outcome for that.
Could it be formalized as a constraint for the algorithms? Like, for example, the algorithm could say that, because where did they pick this 3% from? You could formalize it as saying you cannot treat more than 3% of people.
There are, like, just like the insurance companies, like home insurance and car insurance, there is like a risk equation. They would say we can take as this number of patients with chronic conditions,
Exactly.
and then we don't break the budget for the rest of the people.
Yeah. So
But these numbers are hidden.
I see. Well, we should talk. I don't know. Yeah, Eli.
I mean, there is all this crazy stuff people do when you look up when all your covariates are not observed, or you get point identification sometimes. I just wanted to point that out. There's huge literature. There's graph stuff people do. There's like stuff that proxies people do. So maybe it won't always be associated basically in that case.
Yeah.
That's one thing I wanted to say. The other thing I wanted to say is Ed Kennedy has a really interesting paper on decay. I don't know if you're aware of it. I sent it to you by email about pseudo outcomes, basically using double robust method to stick a pseudo outcome in there.
Is that the one with Rambachan on select?
I think it's a solo author paper actually. Let's see. This one, I have it pulled up here. Yeah, it's just him. It's called optimal doubly robust estimation of heterogeneous treatment effects. I think it's a pretty interesting paper.
Yeah.
I don't think he has minimax rays, but he's getting there basically. So anyways, yeah. Thank you for a wonderful talk.
Thank you.